Hi, my name's Dane Merkel. I'm currently completing my final year project with Waterline Projects. It's an industry-based thesis aiming to develop a model that demonstrates current network performance and some ways that we can adjust what we're currently seeing. During this presentation, I'm going to walk you through one of the problems currently being seen by Australia's national electricity market, predominantly due to solar energy. Some of the current solutions that we see in the industry, a different solution, which is my proposed solution, how that can actually be achieved, what it is exactly that I'm trying to achieve, as well as I'll go through the boundaries of the project, limitations of my scope. So the problem that we're seeing due to the large uptake in solar over recent years is that overall we're having a net reduced electricity consumption. During the day, solar energy is being produced, which is pushing our trough, making a trough in our load profile, whereas when solar is not available over peak periods, we're seeing an increase in peak demand. This is basically creating lower levels of asset utilization, and the lower net demand means that we're selling less units of energy. The higher peak demand, though, means that DNSPs still need to augment their network to supply this peak demand. These costs need to still be recovered, and recovering them over less units of energy sold means that the price is being driven up. This is coined a term that has been known as electricity death spiral. Basically, what happens is the more expensive energy is, the more pressure people see to put on solar or look for alternative methods, reduce the amount of energy they're using, resulting in less energy being sold, resulting in prices having to go up even more. This is a cycle we've been stuck in for a while now. There's a few things available where research is being done into different methods to combat this, but nothing effective is widely available yet. This here, as you can see, is a load profile of the Rockhampton Glenmore substation in summer. This is the power in megawatts, and as you can see, you get your morning peak around here, followed by a bit of a drop, as to be expected, although this is quite a sharp drop, and then we rise over our evening peak, and then we drop off again. The ideal load profile that we would like to see, although not realistic, the ideal load profile is just a flat line providing DNSPs with 100% utilisation. While not realistic, that's what my project is aiming to move more towards. Although it doesn't look that bad here, this is at a substation level. If we go ahead to look at a feeder level, this is in northern parts of Brisbane, we can actually see that some feeder, the red line here is 2014, whereas up here is 2009, 2010. This is when solar was having its largest uptake due to the government incentives, and you can see that during the peak day on a hot day, the amount of solar energy is almost reducing the net demand to zero over this period. What this is also resulting in is a much faster ramp rate being required, which requires expensive peaking stations to be turned on. On the right is another graph, which is actually from California. That is their statewide load profile, and again, the orange line down the bottom here is the most recent versus 2012, sorry, it's predictions. The purple line is 2015, and the blue line is back in 2012. Again, California had a massive solar uptake over this period. They ran a program called Solar Cities, and as you can see, this has had a huge impact. It's actually coined the duck curve because it ducks down so far. The things that are currently being done about it is companies are attempting to integrate solar PV with the grid. University of Queensland, UQ, ran a few projects. They've got a grid integrated solar system at their Gatton campus. They've also installed a car park solar array with battery power. This is aiming to basically offset the effect of solar. That's what the batteries are for, as well as to create a more energy efficient campus there. Another solution is a lot of people are either shifting off grid or attempting to. They're installing solar, things like this, in an attempt to save themselves money. Overall though, this is just helping to contribute to that death cycle, and it's driving electricity costs up. it's developing short-term solutions that benefit an individual user. Over the last 2 decades, Australians have become a lot more aware of trying to be more energy efficient. New technologies and advances in technologies have enabled people to do this. People have been changing their habits, but still, even with all this, we're still seeing the same trends occurring that have occurred elsewhere in the world. A different view on it, which is what my concept model is trying to provide, is a solution that's going to benefit all stakeholders involved in the electricity market, not just the end consumer, not just the distributors, not just generators. Ideally, what we'll do is, by utilising some emerging technologies, in particular batteries is what I'm focusing on, we will try to absorb some of that solar during the day, store it up, and then use it overnight. A little bit different to what is technically what has traditionally been done. Rather than trying to store it and use the energy yourself, form microgrids basically, where a small community can all be connected together, and the load, wherever the load is, the energy can be shifted to there. At this stage, just looking at a concept design, so to prove that this is possible, there will be lots of other hurdles to overcome in the future, such as regulatory issues, how you would go about costing and paying people for supplying the energy, things like that. But the biggest thing that we've seen, the recent announcement of the Tesla batteries has produced pretty big shifts around the world, started a conversation about whether batteries are now becoming viable. Their biggest entry into the market has been they weren't economically viable in most situations. They cost too much. There is now a bunch of Japanese companies entering the battery market, including Samsung, Kyocera, so large companies like that. Tesla Powerwall is going to be shipping to Australia end of this year, early next year. It's already out in the US. They're lithium-ion batteries. My project's also going to focus on the well-known lead-acid battery, as well as another type of battery that's becoming more popular lately, which is a flow battery. Works with a zinc bromide formula, and they're what's actually installed at the UQ car park. So it'll be interesting to see the different results that we can achieve with different batteries. As of July 2015, the Rockhampton region has about 3.8 megawatt of installed PV capacity, and that's about 16% penetration, and there's actually almost 30 megawatt in the entire Rockhampton region. The first one was just Rockhampton City itself. So the way I'm planning on achieving this is I've received some data from Ergon Energy and analysed the current load trends that are seen at Rockhampton. As you saw the graph earlier, that was a hot day in summer. I've also obtained some data for different seasons, and we're going to attempt to model this across different periods of the year, which is where the environmental considerations here come in. Obviously, Rockhampton has quite a high solar penetration all year round compared to other parts of the country, Victoria, etc. So the impact there may not be as big as in other places. Once all this is considered, using MATLAB, I'm going to model the current situation that we have in Rockhampton. Once I've got quite an accurate model of how the network is currently behaving, we'll add in some different batteries and PV configurations. Determine the ideal situation with cost per kilowatt, so the end user can save some money there. And then the idea here is when load is needed, it can be shifted to where it's needed, which will create a better load profile for distributors and transmission companies. And then on top of this, it will help defer the need for network augmentation, so less capital costs, less operational costs for both those companies. And then this can reflect all the way up to generation level, so peaking plants not being required as often, which are the most expensive ones, and a much smoother load profile with lower ramp rates can basically help save everyone involved money. So we're trying to prove that it is possible to shift away from the how can I benefit me model, short-term solutions, to long-term how can everyone benefit. From here, once I've modelled the different types of batteries, We'll evaluate the different outcomes and develop a plan to move forward depending on what the results are. MATLAB was chosen for the modelling based on how powerful it is. There's a lot of support out there for it, as well as a lot of solar battery models already exist. That's the main reason I'm choosing to work with MATLAB. Project is aiming to obviously produce a technical report which will detail the project findings, a model of the seasonal network performance with and without the batteries to show what the benefits can be. Depending on results, a business viability report may be produced for Waterline. This obviously being a workplace project needs some commercial use as well. There'll also be a lot of non-tangible outcomes, personal learnings for myself and the company, as well as starting a discussion in the industry about needing a change. There was a recent conference held by SIGRE where there was a lot of talk about everyone knows that something needs to change, but nothing's been changed yet. A lot of companies are trying to find a solution, and we believe that if we can prove this successful, that this is one of the ways to move forward. As it is still university, one of my biggest constraints is going to be time, so I've had to limit my scope to just a concept model at this stage, so any actual physical implementation of the project is currently out of scope. Depending on the results, that can be a future project looked into, either by myself or someone else. Again, predominantly due to time, the QA of data that I receive is quite difficult. Obviously, I'm analysing the data, and if there's anything that stands out as not accurate, I will flag that, but I'm trusting the sources that I'm getting data from, which are Ergon Energy, Bureau of Meteorology, so reliable sources like that. The other thing is there's many other types of batteries that I won't have time to look at, many that aren't widely available in Australia, such as sulfur batteries, which have huge lifespans, huge power input and output. The problem is they're not quite safe and they're still being developed. They require a lot of heat to run, but which may help suit to the Australian environment, but at this stage not commercially viable. And then there's also other energy storage systems such as flywheels, geothermal, plenty of other things that aren't being considered in this project. The aim of this is just to prove that there is an alternative to what's currently being done. So that's the end of the presentation. If you have any questions, I can be contacted at Dane, Dane.Merkel, Merkel, @cqmail.com. Thank you.